Okay, we will pick up where we left off in the first video. Okay, on topic 1, still introduction to mechanisms. So in this video we're going to start out by talking about degrees of freedom and mobility of mechanisms. Okay, and this is where we kind of start getting into some theory. First, it's important that you understand degrees of freedom. What are degrees of freedom? Well, every body, every rigid link, everything, has a set of degrees of freedom. For two-dimensional scenarios, every unconstrained, it has no constraints, it's just a body, but it's stuck on a plane. It has 3 degrees of freedom. Okay, so it can either translate, you can see the arrow, translate up or translate over, or really translate anywhere in that plane, and then it can rotate about any axis out of that plane. So, any axis coming out of that plane, it can rotate on. So just imagine, you can move like this or you can move like this, okay, on a planar thing. So 3 independent degrees of freedom there. Okay. Now, if it's a body in 3 dimensions, imagine I took it off the screen here, like this piece here. It can move with, if it's not constrained, say it's just floating in air, it has the capability to move with 6 degrees of freedom. Okay, so there's 3 rotations. Okay, as you see there, 3 orthogonal rotations and 3 orthogonal translations. Okay, so 3 translations, 3 rotations, that's 6 degrees of freedom. And so that's true of any body in a 3-dimensional existence. The most degrees of freedom any single body can achieve is 6. Okay, and if it's constrained, it may lose some of those degrees of freedom. Of course, if I fully rigidly lock onto it, it can't move at all. Okay, but I could constrain it so it could only rotate or it could only translate, these kind of things. Okay, but you can never get more than 6 degrees of freedom for 3 dimensions. And for 2 dimensions, you can never get more than 3. Okay, so that's the number of degrees of freedom of a body. Okay, but mechanisms are multiple bodies linked together by joints and pairs. Okay, or multiple links joined together by joints and pairs. Okay, so links are bodies. Okay, and when we talk about a mechanism's degrees of freedom, we're talking about how can it move? How can all of them move simultaneously? With them all working together, basically. So you're kind of adding degrees of freedom together of the different bodies, but removing the constrained degrees of freedom that it can't move with to give the full mobility, it's called, of the mechanism. So mobility is basically how many degrees of freedom the mechanism achieves, okay? And so a mechanism's degrees of freedom are kind of defined as the number of independent parameters required to specify the location and orientation of every link in the mechanism. So that's one way to think of it. I told you, the first way to think of it is like it's kind of, given, this case there's 4 bodies or 4 links joined together. One of them is grounded. See, this includes, you might think, here's 2 different grounds, but one very important point, if you have 2 different grounds, they're one in the same body because they're both not moving, and they might as well be connected together as one single link. Okay, so if you see a bunch of different grounded points, you can treat them all as one single link because they might as well all be connected. They're all not moving, and all the points on them are moving with the same relative speed, which is 0. Okay, so this is 4 bodies connected together. But anyway, getting back to the definition of degrees of freedom, you can look at it as like, okay, you've got these 4 different bodies, they're connected together. And how can the whole mechanism move? What's its mobility? Right? But another way to think about it is this definition I gave you here, which is the number of independent parameters. So in this case, theta can, the angle of this link from this dotted line, theta, can fully define the whole system. Okay, so it really only takes, if I told you this is 20 degrees, then all the rest is determined. You could calculate, you could know it. Okay, so the whole system is determined by that. And so because of that, because there's just one parameter that defines the entire mechanism, that's just 1 degree of freedom. Okay? Another way you can think of it is if I hold some body fixed, does it lock it up or not? And if just by holding one body fixed locks it all up, it usually has 1 degree of freedom. That's kind of a sketchy definition. I'll show you some exceptions to that, but it can be useful to think of it that way. Another way to think of it is how many motors or actuators would you need to fully control the whole mechanism? And that's usually the number of degrees of freedom. So in this case, if I just had one motor turning this, the rest would all move and be determined. Okay? So for this mechanism, this 4 bar is 1 degree of freedom. Okay, so if I look at this mechanism, the 5 bar mechanism, you ask, well, how many degrees of freedom does this have? And 5 bars because, the ground is 1, 2, 3, 4, 5, right? And so how many degrees of freedom does this have? Well, if I provided some theta angle, would it fully define the whole system? Well, no. Say I made this, it looks like it's like a little over 90 degrees. In this case, so say 100 degrees or something. And I said, okay, this is 100 degrees. Could the rest of the mechanism move? Yes, it could. It could move like a 4 bar, right? And so, it needs more than this parameter. Okay. Oh, I thought I'd draw that. But what you need is another angle here to define it, or some angle here. So you need at least 2 independent parameters to fully define and kind of lock up the mechanism, right? Or if I ask how many motors would it take to fully control this, you couldn't fully control this with just one because this part could be flopping around. You'd need a second motor to fully control it. So it's 2 degrees of freedom. And again, going back to our bad definition, but can kind of be useful in some cases, if I held this fixed, can it still move? Yes, it can. So if I held this fixed, can it still move? No, it can't. So there's 2 degrees of freedom because it took 2 things to hold it fixed. Okay? That's one way to think about it. Okay, so the mobility of a mechanism is the number of degrees of freedom that the mechanism possesses. Okay? And I'm going to give you an equation. It's called Kutzbach's equation. It's very, very famous. For determining how many degrees of freedom a mechanism has, what its mobility is, how it can move, okay? And I'm going to derive it for you here before giving it to you because it's actually pretty easy to derive, okay? So this is going to be Kutzbach's 2-dimensional or planar, equation. And so we're going to just look at things in planar land here with planar mechanisms. So you can think, if this is a single rigid body just on a 2-dimensional surface and there's no constraints anywhere, it of course has 3 degrees of freedom. Its mobility m would be 3, meaning it can translate with 2 independent translations and it can rotate out of plane, or with an axis that comes out of plane. Of course, it'll always be rotating in plane. All the points on it will be in plane. Right? So, okay. So I told you, 2-dimensional things have 3 degrees of freedom. Okay? Well, so now what if I have 2 bodies that are just kind of floating in the ether there, and they're not interacting, they're not touching with each other, as you see in the middle here. How many degrees of freedom does that system have? Well, 3 from one of the bars and 3 from one of the other one. So it's 2 times 3. The number of links you have is 2 times 3, the number of degrees of freedom each link can have if it's not constrained in a 2-dimensional thing, 3. That means 6 is the mobility. 6 degrees of freedom together combined. Okay? Now what if we do something interesting and connect these 2 links with a pin joint, as you see up in the top right? Okay? Well, a pin joint kills the 2 translations, right? It only allows a rotation. If you have a body, like think about it, if that top horizontal bar was held fixed, and then you just considered the other one hanging free. If it didn't have a pin joint, you have 3 degrees of freedom. But once you stick that pin joint in it, it kills the 2 translations and it only allows that rotation. So pin joints are a kind of joint because they have 1 degree of freedom. They kill 2 degrees of freedom. Okay, so they allow 1 degree of freedom, but they constrain 2 of them. Okay, so what you do if you're trying to find what's the mobility of this mechanism or this system with 2 links and a pin joint, now assume nothing's grounded, it's just like 2 kind of things chucked in the air like nunchucks or something, that two links connected together with a pin, well, you'd have a mobility of 6, but then you'd subtract the 2 degrees of freedom that are killed by pinning them together, and so that full system would have 4 degrees of freedom. And of course, if you held one of them fixed, like I said, the top bar, you'd subtract 3 more degrees of freedom from that, so it would go down to 1 degree of freedom. Okay? So you can kind of see how we're doing this. Okay? Let me jump right to Kutzbach's mobility criterion. If you didn't follow me there, you should get it from here, from the derivation of Kutzbach. Okay? So this is a very famous equation that you should memorize, have written on the insides of your eyelids, right? N is the number of links in your system. Okay, including the ground. It's the number of all the links. Okay, and then you subtract 1 because you want to get rid of the ground because it doesn't have any mobility to it because it's held fixed. So that's why you're subtracting 1, is to get rid of the ground. So don't like count everything, all pre-exclude the ground because this equation already gets rid of the ground, okay? All right, and then you times that by 3 because each of the links that aren't grounded, meaning this one that's subtracted from it, would if they weren't connected together by joints, they would each have 3 degrees of freedom. So this right here represents all the links that aren't grounded and all their degrees of freedom added together, okay, without any joints. Okay, but now here we're adding joints. J1 is the number of single degree of freedom joints. Again, it has nothing to do with lower pairs, higher pairs, has nothing to do with anything but degrees of freedom. Okay, so if it's a 1 degree of freedom joint, that's a J1. Okay, and you count how many of those are. Now, here's the thing. Why do we subtract it? Well, first of all, when you add a joint, you kill degrees of freedom. That's what joints do. They constrain things but allow other degrees of freedom to remain. But they kill degrees of freedom, so we're subtracting mobility from here. And why do we subtract 2 if it's a 1 degree of freedom joint? Well, because in planar world, right, if you can only have 3 degrees of freedom, and if you have 1 degree of freedom joint, then you're killing 2. So if you have, J1, 1 degree of freedom joints, then that number times 2 is the number of degrees of freedom you're killing. Okay, and then J2 is the number of 2 degree of freedom joints, right? And if it's 2 degree of freedom joint, like I said, the cylinder on the flat, it can slide, but it can also roll. That's 2 degrees of freedom. That would be a J2 joint. That means if it allows 2 of your degrees of freedom, a translation rotation, it's killing the other translation. Okay, the one into the page, or the one that would break the joint. Okay, so 2 degree of freedom joints only kill 1 degree of freedom, so that's why there's a 1 here. Okay, so you can see here, and then of course, if it's a 3 degree of freedom joint, it would be 0 because it's not killing anything, and that would be silly. All right, so it's not even included in the equation here. So you can see for 2-dimensional planar mechanisms, this will tell you the mobility m. Okay, and you can deduce the derivation of that from this line of thought. Okay, so let's test this, try it out. Okay. All right, so let's look at this this structure here. Okay, so you first start. If I say what's the mobility? Well, first of all, I'm sure you're smart enough to know that that's like a truss. It doesn't move. Its mobility is 0. Okay, but let's use Kutzbach and see if it works. Okay, what I just taught you. Okay, so you ask, well, how many links are there here? Well, okay, and remember, include the ground. So there's 1, 2, 3 links. So n is 3. Okay. Well, how many J1 joints are there? How many 1 degree of freedom joints are there? Well, these are all revolute rotation joints. They only get 1 degree of freedom. It's a rotation. So there are 3 J1s. 1, 2, 3. Okay. How many J2s are there? There are 0 because there's no joint that can get 2 degrees of freedom. Okay, so if you plug these numbers into Kutzbach and calculate m, you will indeed find m, the mobility is 0. Okay, so that means that can't move. Now you've got to ask yourself, so is this a mechanism? Let's go back and review some stuff. Well, it does consist of multiple rigid bodies or links. They are connected together by joints. Okay, there is a ground, and it is a closed kinetic chain, but it does not move. It's a structure, so it's not a mechanism. Okay, and consequently, it's not a linkage either, because all linkages are mechanisms. Okay, all right. So let's go to another example here. Here is the slider crank mechanism, and here's what makes it more clear that it's a closed kinetic chain. Let's first do this example again. Is this a mechanism? Yes, it consists of links connected together by joints, there is a ground. It's this guy that goes all the way through there. It's held fixed. Is it a closed kinematic chain? You can clearly see here it is a closed kinematic chain, whereas the other diagram you couldn't see that as clearly. And yes, it does move and it has a mobility. So it's a mechanism. And is it a linkage? Indeed it is, because it consists of all lower pair joints. Okay, lower pairs, because they're all surface-to-surface contact. Okay, so it's a linkage. Okay, but anyway, getting back to Kutzbach, let's use this to find what mobility it is. Okay, you already know it's 1 degree of freedom, but let's calculate this. Okay, so how many links are there? Well, there's 4. There's 1, 2, 3, and the box is 4. Okay, That's how many rigid bodies are in there. Okay? Well, how many J1 joints are there? Well, that means how many 1 degree of freedom. Remember, it has nothing to do with lower or higher pairs or surface area or anything. It's just how many 1 degree of freedom joints. So remember, J1 has nothing to do with lower or higher pairs. That's a completely different concept, okay? J1 has everything to do with degrees of freedom. Okay, so J1, there's 4 of them. There's one of these, one of these, one of these, so that's 3 revolute joints and 1 slider prism joint, and that's 4 joints with 1 degree of freedom. Okay, J2 joints, how many of those are there? There are 0. There's none. Okay, so you plug that in the equation and you will find an M mobility of 1. That means it takes 1 motor to drive this whole system. That means if I hold this one thing fixed, everything will be locked up, and there's just really 1 parameter that input parameter that defines the whole thing. Okay. All right. So that's the mobility there. Okay. Let's look at some other examples. This is a 4-bar. Okay. We already know this is a mechanism and linkage. Okay. How many links does it have? Well, it has N 1, 2, 3, 4. That's why it's called a 4-bar. It has 4 J1s, 1, 2, 3, 4 revolute joints, and they're just a single degree of freedom, which is why we count them as J1s. And then how many J2s? There's none. And so the mobility is 1. Okay, no surprise there. And it just takes 1 motor to drive it. It's 1 parameter to fully define it. If I hold any of these fixed, the whole thing locks up. Okay, great. All right, let's look at this 5-bar mechanism in Kutzbach. Well, how many ends are there? There's 5. That's why it's called a 5-bar. 1, 2, 3, 4, 5. How many J1 joints are there? 1, 2, 3, 4, 5. 5 J1s. How many J2s? There's no 2 degree of freedom joints, so there's 0. And so the mobility is 2 if you plug it in a Kutzbach. And I recommend you do the simple calculation, and you'll find there is a mobility of 2, which makes sense because, like we told before for 5-bar, it takes 2 independent parameters to fully define it. It would take me holding 2 of these fixed to lock the whole thing up, and it would take 2 motors to fully define and drive it. Okay? Okay, so let's look at some more interesting examples here. Okay, so this one's there's a trick in this one. So you ask yourself, what's the mobility of this? You could already visualize this like a truss. It's not going to move. But let's pretend you didn't know that, and let's try Kutzbach here. Okay, so how big is N? Well, okay, let's count the links. 1, 2, 3, 4, 5. Okay, so N is 5. Great. Okay. Well, how many J1s are there? Well, you probably think, well, there's 1, 2, 3, 4. But that's wrong. And that's because, remember, a joint is always a thing that just joins 2 things. It looks like, for instance, for this one, there's actually 1, 2, 3 links that this joint joins. But really, joints or pairs, the reason they're called pairs is because they only join 2 things. They link 2 things together, or a pair, right? And so you'd have to count this one twice, one for this one and one for this one. Okay? And really, if you want to know how many times to count a joint, you can count how many links go into that revolute joint and then subtract 1. That's what you do. However many links go into the circle, you count how many of those lines go into that circle, subtract 1, and that's how many times you count that joint. So same thing with this one. There are 3 lines that go into that circle. Subtract 1, that means you'd count this one twice. Okay, so let's count the J1 joints. There's 1, 2, 3, 4, 5, 6. Okay, so there's 6 J1s, and I've noted here you count these 2 twice. Okay? Okay, there's no J2s, meaning things with 2 degrees of freedom. Okay, and so we plug it in there, and sure enough, Kutzbach says it's a 0 mobility, it's a structure, it doesn't move, and therefore, consequently, it's not even a mechanism, it's not a linkage. It's just it's a truss, basically. It falls under the static category in mechanics. Okay, let's look at this system here. Now, you see these bars are kind of crossing. Just pretend these don't even touch. They don't interact. It's not a joint there. If you just see 2 lines overlapping, you do not assume it's a joint. You can assume they don't touch. Like you can imagine this goes underneath and this goes over on top, whatever. And they don't need to draw anything like the circuit diagram, circle over it or anything. It's just they don't touch. The joints will always be drawn as prisms or revolute joints or however I taught you in the skeleton diagram, okay? Okay, so now let's count all this. So How many links are there? What's N1? Well, there's 1, 2, 3, 4, 5, 6. Okay, so there's basically, you could make that with 6 bars. Okay, so that's, or links. Okay, so that's 6. Okay, how many J2s are there? Or sorry, J1s? Okay, well, again, you wouldn't count just these once, or you think J1 is 4, but that's wrong. You say, how many lines go into each and subtract 1? Okay, so this would be 1, 2, so you count that twice. Okay, count that twice, count that twice, and count that twice. So it's basically 4 times 2, so there's 8. J1 would be 8 there. Okay, and J2, there's no J2, no joint with just 1 degree of freedom. And so now you plug all this into Kutzbach, and sure enough, what do you find? Well, your mobility is, it's -1. What does that mean? Well, certainly if it's -1 mobility, it doesn't move, and you can see there, that's even more trussed up than this. So that's not going to move. So if it's 0 mobility or negative or less, right, then it's static, it's not going to move, it's not going to be a mechanism. But what does the negative number mean? Well, it means it's over-constrained. It means, like, if you took one of these bars out, one of these links out, it would still do the same job of statically constraining it. So anytime, this is how many times over it's over-constrained or it's redundantly constrained. It's also, systems like this are called statically indeterminate. They're static, but they're indeterminate from a math perspective. Okay, they're over-constrained. There's constraints doing the same job. Okay. So something to look for there. Okay, so let's do a really complicated example here. Okay, so all right, this is one. So here's about as complex a skeleton diagram as you'd ever find, and this diagram can be a little tricky. Let's look at this. So first of all, we have a circle here, and we have the hatch lines in the line. Is that a slider joint? No, because it's a circle, you can assume that's fixed to the ground, okay? Now this one, we have a box on a line with hatches, but those hatches are only below the square. Does that mean it's fixed? No, it's not. And I actually probably should have added that to the slide before, because the slide before I had hatches going all the way on the sides as the only acceptable way to slide. But if you have a line that spills out beyond the edge there, no matter where you put the hatches, that means that the line itself is the link that's held fixed. But this is a box that slides with a prism joint on it, okay? So go back and look at that slide and just update in your mind if you have any line that extends beyond the square, whether the hatches are directly below it or on the whole line or just on a part of the line, that whole line is grounded and the box can slide, okay? So this is a prism joint there. These guys are fixed, okay? So, and notice there's a bridge here, and here's a sliding prism joint. That's a link there. So, okay, so with all that in mind, let's use Kutzbach and calculate the mobility. This is where Kutzbach is super valuable, because that would be very difficult to visualize the mobility of a mechanism like this. And this is what you'd find on an exam. Like what's the mobility of a crazy mechanism like this, okay? So let's use it. How many N are there? How many links? Well, remember, you got to count the ground, okay? But you might say, oh my goodness, there's 1, 2, 3, 4, 5, 6 grounds. But no. All grounds are always one link, one body. I could have just drawn these lines together, come up here, drawn it together like there, drawn it together like there, then made one big blob or something, because it's all just one ground. So only count ground once. So that counts as one link, okay? And then, okay, you ready? 2, 3, 4, there's 5, okay, 6, that line, 7 the box, 8 this line, 9 this line, 10 this whole line, and then you count that once because it's bridged together, 11 that line, and then 12 the box, okay, because it's not ground. Remember, it's its own link that can slide on the ground that we already counted. Okay, wait a minute, did I count the right one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, okay, so there's 12. I hope I counted that right before this. But anyway, you saw how I counted it. That's 12. Okay, so 12 links. Let me count it again just to make sure. Okay, so 1 for the ground, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So you can see how I counted that. Okay, so there's 12 links. All right, so how many J1s are there? How many single degree of freedom joints? Remember, it has nothing to do with lower or higher pairs. It has nothing to do with surface area or point or line contact, nothing. Just, it has nothing to do with plane or anything. It has everything to do with the number of degrees of freedom that the joint achieves, okay? So, let's count them, okay? Well, we have 1 from here, 2 from this revolute joint, okay? 3 from that revolute joint, but look, there's 3 lines that go in it. So 3 minus 1, you have to count this one twice. Okay? So here we go. Let's recount. So 1, 2, 3, 4. Count it twice. 5, 6, 7, the prism joint. 8, this revolute joint. 9, this revolute joint. 10, that revolute joint. 11, that revolute joint. Okay? 12, this revolute joint. 13, this revolute joint. 14, that joint, and you don't count it twice because remember this is one thing connected to that. Okay, 15 this revolute joint, 16 this sliding joint or prism joint. So it's 16. I'm going to count it again because it's always confusing. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so J1 is 16. J2, there's no 2 degree of freedom joints. If something rolled or slide or did something, that would be a J2, but there's no J2. Okay, and then you plug that into Kutzbach, and it will spit out M of 1. So it turns out a mobility of 1. That means it would just take 1 motor to drive this whole thing, and if you hold this locked up fixed, the whole thing would be locked up. And so it's mobility of 1. Okay, now where the hold things fixed and gets locked up is confusing, because if I held this fixed, it wouldn't affect anything because this is already like a truss structure in here. Like this whole thing is kind of useless if you look at it. It's like ground with 2 beams connected together. This whole thing's already not moving. And if you wanted, you could actually just get rid of this whole thing and put just a pin joint there on ground and do the whole analysis again, and it would still give you a mobility of 1. So be careful when you're thinking in your mind of just holding stuff fixed and seeing if it locks up to count degrees of freedom. But it can be a valuable thing as long as you do it correctly, right? You're not stupid about it. So notice this is like locked up, okay? 1 degree of freedom of doing it. But if you can't visualize, it's okay. You have Kutzbach. Okay. All right. So let's do this example here. Okay, so here we have, like an egg-shaped link on another link with a ground. Okay, so there's 3 here. And first of all, let me ask you, is this a mechanism? Okay, well, so it certainly, it consists of rigid bodies. There's 3 of them. Okay, and they're connected together by joints, 2 revolute joints, and this is a sliding and rolling joint, meaning this is allowed to both slide, like when I slam on the brakes in a car, the wheels slide, or roll when I keep driving on the wheel rolls. Okay, so it can roll and slide there. Okay, so there's 3 joints. Okay, so it's rigid bodies connected by joints, and there's a grounded joint. That's one critical thing for the definition of a mechanism. It's a closed kinematic chain. You bet it's closed. And can it move? Yes, it can. You can imagine if I put a motor on this and rotated this like egg around, that like link would kind of like ride up and down it as it moves. So it can move, and so yes, it's a mechanism. But now the question is it a linkage? Well, remember, to be a linkage, you have to be a mechanism, but you also have to have all lower pairs. And remember, lower pairs has nothing to do with degrees of freedom. It has everything to do with surface contact. So these 2 are pure surface contact, cylinder and cylinder, but this is just a line contact where they touch. That's a higher pair. So since these 2 surfaces always only touch at a line extruded in the page, that's not a surface, so that's a higher pair, and therefore it's not a linkage. It's a mechanism, but it's not a linkage. Okay. Let's do Kutzbach on it, okay? So let's see, what is N? Well, N for this case is 1, 2, 3. So N is 3, that's easy. How many J1s are there? Well, there's really just, and remember, J1 is has nothing to do with higher or lower pairs. It's the number of degrees of freedom. So there's 2 1 degree of freedom joints. 1, 2. So J1 is 2. Okay? So what is J2? How many 2 degree of freedom